Welcome everyone. My name is Xinying, and I am presenting our work on learning analytics in a digital learning game. This work is in collaboration with Hui, Professor John Stamper, and Professor Bruce McLaren. I would like to start with introducing digital learning games, which are a new kind of educational technology where the learning materials are embedded in a game environment. It can be a powerful tool to promote learning by engaging students with the interactive environment. While there were initial concerns about digital learning games' effectiveness, recent research has shown about its benefits over traditional learning approaches in rigorous randomized experiments. For example, a meta-analysis in 2016 showed that game conditions promoted significantly more learning than non-game conditions with equivalent knowledge content. Also, the augmented game designs with more learning-oriented features were more instructionally effective than standard game designs in promoting learning. While this prior research has demonstrated that digital learning games can enhance learning, the next step is to examine how they do so. In particular, even though the common measures of pre-test and post-test scores are necessary to evaluate students' transferable learning, they are inadequate to address many questions about how learning takes place during the game. Therefore, the question we want to ask is how to assess students' learning behaviors, which are often intertwined with game behaviors. For example, these students get just enough practice from the game, these students get more practice than necessary, and how does the in-game learning correlate with the test performance? More specifically, our first and core research question is, how do we know whether students have learned enough or needed more practice at the end of their gameplay? Having examined students' in-game learning, we then looked at how it related to the test performance after the game, and it comes to our second research question: what factors affected students' post-game performance? Furthermore, given the game's dual goal of promoting both learning and enjoyment, do in-game learning metrics also relate to students' enjoyment in any meaningful way? To dig into this part, we raised up our third research question: which factors affected students' enjoyment ratings after the gameplay? We try to answer these questions in the context of Decimal Point. Decimal Point is a digital learning game that teaches decimal numbers and operations to middle school students. The game is an amusement park metaphor with different theme areas, for example, the haunted house and the Wild West. Decimals are critical for students to master in order to advance to more complex mathematics, and many people struggle with decimals even into adulthood. In each theme, there are a variety of mini-games that target the common decimal misconceptions. In general, there are 5 types of mini-games activities in Decimal Point. The first is number line. And number line game is about locating different decimal numbers on a line. The second is addition. Addition game involves adding 2 decimal numbers. The third is bucket. Bucket game targets at comparing given decimal numbers to a threshold number. The fourth is sorting, and sorting game aims at sorting a given list of decimal numbers. And the final one is sequence. Sequence game involves completing a sequence of decimal numbers. Our data comes from a prior classroom experiment at 3 middle schools in a Midwest city in the US. It includes 159 students in total after removing the outliers and those who did not finish all the materials. You can see the step-by-step procedure here. So the students finish their pre-test and 2 surveys, followed by the gameplay, followed by the evaluation survey, and finally 2 post-tests. In order to answer our research questions, we built several metrics to measure the key variables. For learning, we divided into 2 types: in-game learning and post-game learning performance. To measure the in-game learning, we get each student's final mastery probabilities. The key Cs we measured here are the 5 minigame types. We settled our mastery threshold at 0.9 and tracked students' learning progress in these cases by Bayesian knowledge tracing. To measure the post-game learning performance, we use test score from post-test and delay post-test, which is taken 1 week after the post-test. Each test consisted of 43 items for a total of 52 points. You can see the example test item here in the last line of the slide. To measure the enjoyment, we use the average response scores of the enjoyment items in the evaluation questionnaire that students take right after completing the game. It covers these 3 enjoyment dimensions: 3 questions for affective engagement, 5 questions for game engagement, and 6 questions for achievement emotion. These questions have been varied by prior work, and their reliability on our data has also been confirmed in the prior study. Along with the in-game measurements, we also use demographic survey responses as features for modeling the post-game learning and enjoyment. In particular, students reported their age and gender as well as their ratings to survey items about their background information.
Alright, I will now present the results of our analysis. To investigate the first question of how well students learn in the game, we looked at a number of different perspectives. First, we plotted the distribution of students based on the count of master skill. So here we see that by the end of gameplay, there were 4 students who did not master any skill. The majority mastered between 2 to 4 skills, and only 26 students mastered all 5 skills. So it looks like some skills are mastered only by few students and are potentially more difficult than others. To study this conjecture, we next looked at how many opportunities each student who mastered a skill took to reach mastery in that skill. So the violin plot here shows the distribution of opportunity count until mastery in this skill. We see that number line and sorting took the longest to master at around 5 opportunities on average. So these are indeed the more difficult skills in the game. On the other hand, students have to play at least 24 minigame rounds, so we were wondering what they did after reaching mastery in a skill. Did they continue to practice that same skill, or did they switch to a different skill? And we found that students mostly continue practicing the same master skill. In fact, depending on the skill, between 20 to 80% of a student's practice opportunities could be considered over practice, meaning that they took place after the student had reached mastery. So that concludes our EDM learning analysis. Our next research question is which factors affect the students' post-game performance? To answer this question, we looked at 19 factors related to students' background and in-game learning and can be used to model post-test and delay post-test score. So here's our full list of features. Note that there's no guarantee that these features are sufficient to model test performance, but as a first step, we would like to see how effective they are. So based on these features, we perform forward feature selection with a linear regression model in order to select the feature subset with the best cross-validated mean square error. We then ran another linear regression model on the whole dataset using the selected features to predict post-test and delay post-test score. Finally, we evaluate its adjusted R-square as our metric for goodness of fit. Our results show that for post-test score, only 3 features are needed to get the best mean square error, namely pre-test score, bucket, and sorting mastery. The delay post-test score model incorporates 2 additional features, number line mastery and gender. Altogether, they account for about 74% of variance in the test scores, so we could say our learning model performs fairly well. For our third research question, which investigates factors that affect enjoyment ratings, we ran the same feature selection and evaluation procedure, but used the students' enjoyment ratings as the dependent variables. So the table here shows that the selected features and performance of each model. An important observation here is that unlike the learning models, these enjoyment models have very low R-square, which means that they don't capture the enjoyment ratings very well. We will therefore not dive deep into the relationship between these features and game enjoyment. Let's now discuss the results we have found. First, we saw that among the 5 skills in the game, number line and sorting are the most difficult. One possible reason is that students may face more than one misconception when dealing with these skills, and even when they resolve one misconception, they might end up shifting to another instead of arriving at the correct understanding. So to address this issue, we would need more refined knowledge tracing methods to track the students' misconceptions alongside their KC masteries, as well as more in-game instructional support, such as explanatory feedback and error messages. Our second finding is that only 16% of students managed to master all 5 skills, while overpractice was very common. So one possible reason is that the game environment did not indicate when mastery is reached, and so students just picked the games that were easy for them. To solve this issue, the game could provide a skill mastery indicator and also suggest which skill to practice next so that students could optimize their learning. When predicting post-test performance, we found that sorting and bucket masteries are significant predictors of both post-test and delayed post-test scores, while number line is also a significant predictor of delayed post-test score. So the lessons we learned here is that these cases are likely the differentiator components in the test, separating the students with high scores from those without. Therefore, the game should provide more instructional support for these cases, specifically to help students learn better. When predicting students' enjoyment, however, we were not able to get useful insights because our models did not perform well. In this case, a possible explanation is that our starting feature sets are insufficient because they only capture aggregate data points, whereas prior work on effective modeling has employed many more fine-grained features such as interaction trace, decision-making time, and social engagement profile, which we could try to adopt in our future analysis. So in conclusion, our key insights are as follows. First, sorting and number line are important skills for test performance but need more instructional support to master. Second, students did not regulate their learning well and often engage in overpractice. Third, we need more fine-grained features to capture students' enjoyment in the game. These insights can be derived from log data alone and would serve as useful metrics to assist digital learning game researchers in evaluating and improving their own games. In a broader context, we would also like to advocate for efforts in building learning games that can optimize student learning while retaining their core value as a playful environment where players are free to exercise their agency. We believe that addressing this question is an important step for future work in the field. And that concludes our presentation. Thank you for your time. We look forward to hearing your feedback.